All right, for this problem we have three random variables this time, x, y, and z, that are independent and uniformly distributed on the region between 0 and 2. And the question is to find the probability that x, y, and x is greater than or equal to the product of y and z. All right, so for this problem, it involves three random variables, and so the problem involves a triple integral as opposed to a double integral, as we've seen in some of the problems in the past. Now, how are we going to do this one? Well, I'm not going to draw the region of integration completely. That would be drawing a region in 3 space, and I don't think I would draw the region very well. But I can at least get a start on this. So let's just simply take a look at the y times z part. Okay, so let's make this one the z-axis and this one the y-axis. Now, I want x to be greater than or equal to the product of y times z. Also, x must be something between 0 and 2. So if the product of y times z is less than 2, then that's possible. If the product of y times z is less than 2, that's possible. So let's draw the graph of y times z equals 2, or y is equal to 2 divided by z. So that's the graph of hyperbola. And here's going to be 2 up here, that's 2 here. And so this is going to be the point 1, 2, and this is the point 2, 1. Okay. Now, if the coordinates y, z fall over here, then y times z has to be greater than 2, and that will not be possible over here because x must be less than 2. So I don't worry about this. I'm scratching this out. This is not going to be part of the domain. So I'm not going to be using the part here that's being scratched out. So I have to take a triple integral over, as far as the y and the z are concerned, over this part here. Okay, so first off, let's now get the density function, x, y, z. That will be equal to the product of the three marginal densities, because they're independent. And because they're uniform, each one of these will be 1 over b minus a. So in this case, 1 over 2 minus 0. So 1 over 2 minus 0, 1 over 2 minus 0. And so the joint PDF will simply be equal to 1/8. Okay, now let's figure out this integral. Okay, first as I can see here, if I'm going to integrate as this part of my domain, I have two cases to worry about. First case is going to be this part over here when z is between 0 and 1. So in this part over here to the left, the z coordinates go from 0 to 1, and the y coordinates go from 0 to 2. Now I want x to be greater than or equal to the product of y times z. And so the smallest that x can be is y times z, and the biggest that x can be is 2. So I want to take 1/8. X goes between y times z and 2, and then y goes between 0 and 2, and z goes between 0 and 1. Okay, so that's going to be the triple integral, where the base is this part over here. And then if I imagine coming out of the board the x-axis, x would integrate from y times z to 2. So that's a complicated region in 3 space, which it's a little easier just to think of the base of the region. Next, I have the region here from 1 to 2. If z goes from 1 to 2, then the cut on the y-axis, the cut on the y-axis is going to go from 0 to 2 over z. And then finally, the x-coordinate must go from y times z to 2 as before, 1/8 dx dy dz. So that is the setup for the two triple integrals that I must compute in order to compute this probability. Okay, now we just do it. We have integral from 0 to 1, integral from 0 to 2. The inner integral is 1/8 x evaluated from 2 to y times z, dy dz. Then integral from 1 to 2, integral from 0 to 2 over z, and then again 1/8 x evaluated from 2 to y times z, dy dz. That's equal to integral from 0 to 1, integral from 0 to 2. Okay, then plugging in, I'm going to make life a little bit easier and pull the 1/8 out. Then plugging in, I've got 2 minus y times z, dy dz. And same thing over here, 1/8, integral from 0 to 1, integral from 0 to 2 of 2 minus y times z, this should be 2 over z, dy dz. Okay, then I integrate with respect to y. I've got integral from 0 to 1. Then integrating with respect to y, I get 2 times y minus y squared times z over 2, evaluated from 2 to 0, dz. And I forgot the 1/8 out here. Plus 1/8, integral from 0 to 1. 2 times y minus y squared z over 2, but this time the limits of integration are 2 over z to 0, dz. Okay, so doing the integral, we get integral from 0 to 1. Plugging in 2, for y, I get 4 minus 4z over 2 minus, and then if I plug in 0, I get 0 minus 0 dz. Plus, over here, 1/8. Plugging in 2 over z for y, I get 4 over z minus 4 over z squared times z over 2. Then plugging in 0 for y, I get 0 minus 0. And then I need to take the integral from, that's a mistake here, this should be from 1 to 2. That's integral from 1 to 2. This will be integral from 1 to 2 dz. Okay, so integral of 1/8, integral from 0 to 1, 4 minus 2z dz, plus 1/8, integral from 1 to 2, and this simplifies as 2 over z dz, so that'll be 1/4 on the next step. Okay, now we have two more integrals to compute. We have 1/8, 4z minus z squared from 1 to 0. Then I have 1/4 natural log z evaluated from 2 to 1. And so plugging in, we get 1/8, 4 minus 1 minus 0 minus 0. Then 1/4 natural log 2 minus natural log 1. And so that finally ends as my final answer of 3/8 plus 1/4 times the natural log of 2. And so the probability that the x-coordinate is greater than or equal to the product of the y and z coordinates will be this answer, 3/8 plus 1/4 times the natural log of 2.